My name is Hernani Lopez, and the title of this presentation is on the use of finite differences for vibration-based damage localization in laminated composite plates. Laminated composite materials are in the center of modern materials development, with extremely strong fibers being combined with resins to form versatile and efficient engineering structures. Composite materials have a much lower thermal expansion than steel and aluminium, and a higher specific stiffness, strength, and fatigue resistance. However, the advancements made in this development must be accompanied by equally advanced methods for damage detection, since this type of materials develop inherently unique damage and failure modes. In the last decades, vibration damage localization methods, which use natural frequencies, mode shapes, or modal displacements, and other dynamic characteristics, have been extensively applied. Among these methods, the ones that allow the localization of damage with success rely on derivatives of mode shapes, namely their second-order derivative, which gives the modal curvature. However, and as we will see, other derivative orders can also yield successful damage localizations. The aim of this work is to further the use of modal shapes and their spatial derivatives to damage localization in laminated composite rectangular plates. The damage localization methods used are implemented using ANSYS and MATLAB. Initially, finite element models of composite plates in undamaged and damaged states are created, and a modal analysis is carried out in ANSYS. The results of this modal analysis are exported to MATLAB, where the derivatives are computed, using finite differences, and the damage indicators are evaluated. Two laminated composite plates previously analyzed by several researchers were modeled and, subsequently, the damage localization procedure is carried out. The first plate, studied by Moreno Garcia and colleagues, has the size and mechanical properties listed in this table. Only one damage scenario with an area of 40 mm x 40 mm, which is located at the center, is considered here. The plate is clamped on all edges. The damage model is defined by this equation, where uppercase D superscript E is related to the stiffness of the laminate in element E. According to this equation, the stiffness reduction is measured by the damage parameter lowercase d superscript E. This damage parameter is set to 0.1 in the elements at the damaged area, which is also the value used by Moreno Garcia and colleagues. The damage indicators are defined as the absolute difference of the derivative of order p of the displacement in the damaged state, defined as W tilde, and the undamaged state, defined as W. The subscript Q denotes the mode shape that is differentiated. Since p equals 1, 2, 3, or 4, we will have 4 damage indicators, one for each derivative order. Each one of the derivatives is approximated by a central finite difference of increasing order, as shown in these equations. The spatial sampling or step of the finite differences, h, is equal to the size of the elements. The analysis of the displacement and rotation of the plate yields no relevant observations, as the damage doesn't seem to cause any major differences between the undamaged and damaged modes. The undamaged and damaged curvatures show only a small difference, being the value of the curvature higher at the damaged area. However, the third derivative of the displacement has a visible peak on the center of the plate. This demonstrates that higher order derivatives are much more sensitive to damage. Indeed, the fourth order derivative of the displacement of the plate in the damaged state clearly shows peaks at the damage location, where we have the values of an order of magnitude higher than the values of the fourth order derivative of the undamaged plate. The 4 damage indicators were evaluated using the first mode, Q equals 1, and second mode, Q equals 2. These plots show that the location of damage becomes clear with the successive order of differentiation of the displacement. Indeed, with P equals 4, we have all the peaks at the center of the plate, in both modes, Q equals 1 and Q equals 2. We can also observe that the damage indicators, with P equals 1 and P equals 2, give a larger area than the real damaged area and high values at undamaged areas. This is more obvious for mode 1, Q equals 1. Although the influence of all the first 10 modes was studied, we only present here the results with modes 1, 2, and 4. This will be enough to show that the results with lower order derivatives have a great dependency on the mode selected. However, as we will see shortly, this kind of derivatives are more resilient to the presence of experimental noise in the data. So, as an example, we see that the damage indicator based on differences in rotations of the second mode gives peaks concentrated at the center of the plate, whereas the fourth mode presents several humps in undamaged areas. These humps are less significant for the damage indicator based on differences in curvatures, as shown here. Here, we can see that the use of differences in the third-order derivative of the displacements leads to clear peaks at the damage location, and very small values of the indicator in undamaged areas. If one uses the damage indicator based on differences in the fourth-order derivative, we get successful identifications with both mode 1 and mode 4. To mimic experimental conditions, and to test the resilience of the damage indicators, different noise levels are introduced in the displacement of the damaged plate. NL is the noise level and norm RND is a function that generates random numbers with a normal distribution, with zero mean and standard deviation of 10 up to -6. It can be seen that the damage indicator based on the rotations is not much influenced by the noise. We also can see a satisfactory identification in the presence of noise, with the damage indicator based on the curvatures. However, when we apply the damage indicator based on the third-order derivative, some dispersion of peaks is observed in the undamaged areas. The results obtained with the damage indicator based on the fourth derivative present the maximum values for a noise level of 10 that differ in one order of magnitude from the ones obtained without including noise. Furthermore, for this noise level we even have a false positive at the corner of the plate. The laminated composite square plate studied by Naidu and Ratnam in 2020 as 3 damage scenarios. All damage scenarios have a damaged area of 20 mm times 20 mm, but each damage scenario has a specific location, center, and upper right. The plate is clamped on all edges. The damage indicator, used by Naidu and Ratnam, is based on the difference of the damaged curvatures, kappa tilde, and undamaged curvatures, kappa, being each one of these curvatures, the sum of the curvatures in x and y directions. Both curvatures, kappa xx and kappa yy, are computed by applying the second-order central finite difference formula to the displacements, w tilde and w. This slide shows that the 3 damage scenarios are clearly identified, since the highest values of the damage indicator are observed at the center, for damage scenario 1, at the upper center, for damage scenario 2, and at the upper right, for damage scenario 3. Another characteristic of these results, that is worth noting, has to do with the values of the indicator for the different damage scenarios. Indeed, for damage scenario 1, we have peak values which are 1 order of magnitude higher than the ones observed in the other 2 scenarios. Thus, once again, we observe the variation of damage detectability with the mode shape. It is worth comparing the results reported in the paper of Naidu and Ratnam, shown at the top, and the present ones, shown at the bottom. As we can see, there is a clear similarity between our damage localizations and the ones obtained by Naidu and Ratnam. To end this presentation, a few conclusions and ideas for future developments will be highlighted. As we have seen, several damage indicators found in the literature were used to localize damage in 2 laminated composite plates. The results with all damage indicators are comparable in terms of quality, in particular, if the level of noise is low. It was found that the detectability is higher when the damaged areas coincide with areas where there is high displacement, or curvature areas. The damage indicators based on higher order derivatives are more sensitive to noise, having a noticeable negative impact. Another issue that is observed consists in the dependency of the indicator's values on the location of the damage for a specific mode. Some future developments are being considered, namely, complete the study of the influence of the mode shapes, noise levels, and damage location. This will imply the definition of appropriate parameters to measure these influences. Since composite materials have their own kind of damage mechanisms, more suitable damage mechanic models will be implemented. Other type of structures are also going to be analyzed by applying the present damage indicators, and others that will be defined. Finally, we aim to develop and apply a complete approach of damage identification, by acquiring experimental modal parameters, such as modal rotations, and post-process these measurements with the proposed damage indicators. Thank you for your attention.